So we are now in Module 6. Module 6 is all about plane frame. So we talk about plane frame. It is defined as the two-dimensional assemblage of straight members connected together by rigid or hinge connections and is subjected to loads and reactions that lie in the plane of the structure. So of course, a structure that is subjected to an external load. So under this action, the members of the plane frame may be subjected to axial forces like the members of the plane truss, as well as a bending moment and shears like the members of the beam. So we have to take note that members of frames are usually connected by rigid connections, although hinge connections are sometimes used. So we're going to analyze, we have to develop the analysis of rigidly connected plane frames based on the matrix stiffness method. So a plane frame is actually divided into members and joints so that all the members are straight and prismatic and all the external reactions act only at the joints. So we have to consider this example. So for this illustration, so we have an actual frame. So if you're going to observe, the actual frame consists of three members. However, since the member one is actually this portion, this member is not uniform all throughout. So it is subdivided also into, it is divided into two members. So if we're going to have now, if we're going to count the number of members for this plane frame, there are four members of the plane frame. So we have here one, you have two, you have three, and of course you have 4. So for this one, we have to identify our global and local coordinate system. We have to take note that the process of identifying the global and local coordinate system is similar to what we have done in our plane truss. So for this one, on the same manner, for our global coordinate system, so identify you considering the whole structure. So we have here our x and you have our y. So this will be our origin for our global coordinate system. And for the local coordinate system, of course, this is per member. So this is also known as local coordinate system. So we have to consider each member so that you could identify the local coordinate system or the member coordinate system. So same with the plane truss. So for this one, we have now identified our local and global coordinate system. So we have here 1 as a subscript for the first, if it belongs to the first member. So 2 refers to the second member, 3 refers to the third member, and 4 refers to the fourth member. Now, of course, when it is subjected to an external load, so there will be deformation. So this is now an illustration for the deformation formed and because of the external load that is acting. So basically, if we're going now to identify our degrees of freedom using the symbol arrow and arrow with a slash for our restraint coordinates. So we're going to start with joint 1. So this is our joint 1. We number that joint 1, joint 2, joint 3, joint 4, and joint 5. Now for joint 1, this is fixed, so there is no degrees of freedom. For joint 2, of course, there is no support. This is a free joint, so which means that there will be 2 degrees of freedom. So we have to take note, class, that for the degrees of freedom, for the plane frame, for our degrees of freedom, this is subjected to displacement known as translation and rotation. So which means that we have rotation and translation for the displacement on our plane frame. And for our plane frame, there is translation along x and y direction and rotation about the z-axis. So which means that to specify actually, these are the translation and rotations, this three displacement, translation along x and y direction and rotation along about the z-axis are needed to completely specify the deformed position. So we have to take note that for every free joint, there is 3 degrees of freedom. So if we're going to identify now, so joint 1, there is no degrees of freedom since this is a fixed support. Joint 2, there is no support, it's a free joint, so which means that we have 2 degrees of freedom along x and y direction, translation, and we have rotation about the z-axis. So for this one, we have to number again, same with what we have done in the previous discussion. X direction, translation first. You have to number translation first, then along, for this one, along X direction, followed by Y, then you number rotation. So for this one, you have 1, 2, and 3. So we have 3 degrees of freedom. Joint 3 is also a free joint, so which means we also have 3 degrees of freedom. So you have 4, 5, and 6. Now at joint 4, this is also a free joint, so which means you also have 3 degrees of freedom. So you have 7, 8, and 9. Now for joint 10 is a pin support, or this is a hinge support, so which means that there is no translation along x and y direction, but there is rotation for plane frame. So we number this as number 10. So if we're going to if you're going to identify the number of degrees of freedom, so which means we have 10 degrees of freedom. And if you write this in matrix form, so which means that D is equal to d sub 1, d sub 2, d sub 3, d sub 4, d sub 5, d sub 6, d sub 7, d sub 8, this of 9, and of course we have this of 10. So we have now here our identified degrees of freedom, so which means that we have here 10 degrees of freedom. Now we have identified our degrees of freedom, so which means that we have now to identify our restraint coordinates. So which means we're going to go back to the joints wherein there is no degrees of freedom. So going back to joint 1, so there is no degrees of freedom along about x and y and about z axis. So which means we have restrained for x and y coordinate and restrained also for our about the z-axis. So which means we have here, we have to number. So if we're going to number here, you have to number first along x followed by y, then our rotation for the restrained coordinates. It was restrained from moving along x and y direction and about the z-axis. So we have here, we ended up with 10 for the degrees of freedom. So we have here 11, we have 12, and 13. Now we go back to joint 5. So there is also restrained coordinates. So along x and y direction. So there is no translation to this. So which means that we have 14 and 15. So similar, we have an arrow to represent degrees of freedom and an arrow with a slash to represent our restraint coordinates. So we have now identified our restraint coordinates. So if we're going to identify our action vectors is equal to the number of restraint coordinates. So which means in matrix form, our reaction vector denoted by capital R, that will be, we start with R sub 11, R sub 12, R sub 13, R sub 14, and we have R sub 15. So which means that we have now our restraint coordinates. Now for our joint load vectors is denoted by P, which is in the location and position of our degrees of freedom. So which means that the number of joint load vectors denoted by P is equal to the number of degrees of freedom. So which means that we have here P sub 1, P sub 2, P sub 3, P sub 4, P sub 5, P sub 6, P sub 7, P sub 8, P sub 9, and P sub 10. So we have now our joint load vectors. Now we move on to member stiffness relations in the local coordinate system. So we have to take note that when a plane frame is subjected to an external load, members deforms and internal axial forces, shears, and moments are induced at its end. So this is, which means that for every plane frame which is subjected to an external load, each member will deform and internal forces as well as shear and moment forces are induced at its end. So for example, we have here member M. If we're going to isolate member M, so we have now the member forces and displacement in the local coordinate system. So we isolated member M from our plane frame, and due to an external load, of course, there is a displaced position. So as we're going to identify our forces that will be acting on our uh, member of the plane frame. So we have, of course, we have the internal axial force, we have the shear force, and we have the moment force. So this one is, so which means that for every member, there are six, actually. There are six degrees of freedom. So, which means that due to an external load, there will be displacement. There will be three displacement at both ends of the member. So translation along x and y direction and rotation about the z-axis. So those are needed to specify the displaced position of each end of the member. So which means that each member will have a total of 6 degrees of freedom. So that 6 degrees of freedom are the axial forces. You have the axial force, you have internal axial force denoted by Q sub 1, you have the shear force denoted by Q sub 2, and of course you have your moment force denoted by Q sub 3. So this is present at the beginning of the member and at the end of the member. So this one is the beginning of the member, this one is the end of the member. So to number that one, so we have to number first our internal axial force, which has Q sub 1 along x direction, then followed by our shear force Q sub 2 along y direction. So then we have our moment force denoted by Q sub 3. Then at the end of the member, similar procedure. So you have here Q sub 4 to represent our internal axial force. At the end of the member, then we have our shear force at the end of the member, so Qs of 5, and of course you have your moment force denoted by Qs of 6. So we have now identified our forces that is induced at both ends of the member. And of course, for this one, so which means that we also have 6 displacement for each member. So which means that we have member end force, member end displacement in the local coordinate system denoted by U. So there will be 6 member end displacement for each member. So those member end displacement in the local coordinate system is denoted by U. So you have to number again along x direction. So you have your U sub 1. Then along y direction, so you have your U sub 2. And you have here due to rotation, so you have here U sub 3. Then that is at the beginning of the member. At the end of the member, similar procedure. So which means that you have here along x, U sub 4, member end displacement along y, you have U sub 5, and member end displacement due to rotation is U sub 6. So which means that for every member for a plane frame, there would be 6 forces that will be induced at both ends of the member, and there will be 6 member end displacement at both ends of the members. So 6U and 6Q for the plane frame in the local coordinate system. So there will be 6 member end displacement, and 6 member end forces in the local coordinate system for a plane frame.